This is your presenter Asloob Mudassar, and I am presenting slide number 75 of the course on laser physics. The question is, in the designing of laser resonators, geometric optics under Paraxial approximation is sometimes quite useful. Derive the matrices of useful optical components under Paraxial approximation using geometric optics domain. Also discuss the characteristics of the matrices. The answer is, a general optical system is shown in figure 1, which has its optical axis along the z-axis. The first surface of the optical system is located at z is equal to z1, and the second surface is located at z is equal to z2. So consider the figure. The caption of the figure is propagation of array through a general optical system. Array R1 is incident on an optical system, where R1 is the value of the vector at the input plane, that is at z is equal to z1 plane of the optical system, and the vector R1, that is the ray R1, makes an angle theta1 with the z-axis of the optical system. The emergent ray from the optical system is represented by the ray R2. So R2 is the value of the vector at the output interface, that is at z is equal to z2 plane, and the ray R2 is shown to make an angle theta2 with the z-axis. The optical system may consist of a single element or may consist of multiple element systems. Array is represented by a vector R1 is incident on the optical element at z is equal to z1 with the coordinates R1 and theta1, where R1 is the value, where R1 is the magnitude of the vector R1 and has its value at the plane z is equal to z1. The emergent ray exits the optical component or the optical system at the plane z is equal to z2 with the coordinates r2, theta2, where r2 is the magnitude of the ray r2 at the plane z is equal to z2, and theta2 is the angle that it makes with the optical axis or with the z-axis. You know that here theta1 will be measured according to our sign convention. Theta1 will be measured positive, whereas theta2 will be measured negative, because if you look at the point, which is the point of rotation for the R1 vector, the point where the vector intercepts the z-axis, this is the point of rotation of the vector R. So if you rotate vector R so that it is aligned along the z-axis, then you need to rotate R1 in the clockwise fashion. And if you are rotating it in the clockwise fashion, then theta1 will be measured as positive. But you see that here, in order to make the ray R2 to inclined with the z-axis or to a plane parallel to the z-axis, then R2 must be rotated counterclockwise and theta2 will be taken as negative. Because if you want to make R2 vector parallel to the z-axis, you need to rotate the vector R2 in the counterclockwise direction. So theta2 will be measured negative. Whereas if you want to align R1 parallel to the z-axis, you would rotate R1 in the clockwise direction and theta1 will be taken as a positive. These are the sign conventions that we have adopted in the analysis of the optical systems. Theta1 is taken as positive because R1 needs to be rotated clockwise to coincide with the z-axis, where theta2 is taken negative because the R2 vector needs to be rotated anti-clockwise to coincide with the z-axis. Paraxial ray approximation means that theta1 and theta2 are small angles such that sine of theta I is the same as tan of theta I, and both are equivalent to theta I. Because theta I is a small angle, so that sine of theta I is equal to theta I, and similarly tan of theta I is equal to theta I. These are the approximations under which these trigonometric equations are simplified to their angles. These are called the paraxial approximations, that is the small angle approximations. And this equation, that is the sine of theta I equal to theta I or tan of theta I is equal to theta I, holds for I is equal to 1, 2. So I will stand for the ray 1 and R2 will stand for the ray 2. It is assumed that the ray will travel in a straight line between the two planes. So you see that here we have the plane Z1 and Z2, and we are assuming here for the moment that the ray will travel between these two planes in a straight line. The input variables R1 and θ1 and the output variables R2 and θ2 will be related through a linear transformation under Paraxial approximation. That is, R2 can be written as R2, you see that is the output at the Z2 plane, and R1 is the value at the Z1 plane, and optical system could be represented by the matrices ABCD. So we are writing that R2 is equal to A times R1 plus B times θ1. And similarly, θ2 will also be written as C times R1 plus D times θ1. You see that R1 and θ1 are our inputs and R2 and θ2 are our outputs, and A, B, C, D are the elements that represent the characteristics of the optical system that we have just mentioned. So equation number 1 and equation 2 are our two equations. These are the linear equations because these involve one power of R1 and power of θ1 has a power of 1. So these are the linear transformation equations. Now R2, θ2 are unknown and R1, θ1 are known. A, B, C, D are determined by the nature of the optical element. The previous two equations can be expressed in the matrix form as so the matrix representation of these two linear equations is given in equation number 3, which is R2 θ2 is equal to the matrix A square matrix of 2 by 2 of elements A, B, C, D, and then 2 by 1 matrix containing R1 and θ1. So this is our matrix representation of the equations 1 and 2. Next we discuss the free space propagation. You see that here we have discussed the general system. This system, which we have represented as an optical system, is a general system. We don't know the characteristics of this system, but we just mentioned that the characteristic of this optical system will be determined by 4 elements, that is A, B, C, and D, and we have represented inputs R1 and Rθ1 in terms of the unknown quantities R2. We have represented the unknown quantities R2 and θ2 in terms of the known quantities R1 and θ1, and we have represented them. The two equations have been represented in terms of the matrix representation of the system. So R2 and θ2 is a matrix containing unknowns, and R1 and θ1 is the matrix that contains the known quantities, and A, B, C, D will determine the characteristics of the optical system. However, in this case our optical system is general, so we have not evaluated the value of A, B, C, and D. Next we discuss the free space propagation of array by a distance delta Z is equal to capital L. A ray is incident on the plane Z is equal to Z1 with coordinates R1 and θ1. The same ray leaves the plane Z is equal to Z2 separated by the distance delta Z is equal to capital L. That is, delta Z is equal to capital L is the distance between the plane Z2 to the plane Z1. That is, the Z2 plane is located at a distance capital L from the plane Z1. So Z is equal to capital L from the first plane with coordinates R2 and θ2. So the ray 2 has the coordinates R2 and θ2 when it exits the Z is equal to Z2 plane. Clearly θ2 is equal to θ1. Look at the figure. The ray is traveling between the plane Z is equal to Z1 and to the Z is equal to Z2 plane. So you see that since it is a free space propagation, the light is not diverted, or the light has not changed its direction. It is traveling in the rectilinear path. So it means that the angle made by this ray at the position Z is equal to Z1 is the same angle as made by the same ray at the location Z is equal to Z2. So the angle theta is the same for this straight line, or for this ray traveling in the straight line. So we have clearly θ2 is equal to θ1. Also from the triangle shown in figure, 2, that is this triangle under paraxial approximation. So you see that we have this triangle. Now look at, we have specified the plane Z is equal to Z1 and Z2. These are the two planes. And on the Z1 plane we have the two values of the input ray, that is R1 and θ1. These are assumed to be known quantities, and at the plane Z2 we have the two parameters which are unknown, that is R2 and θ2. These are the unknown quantities. And the ray of course initially makes an angle θ1 with a plane with a line parallel to the Z axis. So the distance delta Z is equal to capital is as the separation between the Z is equal to 1 to Z is equal to 2 plane. And you know that in this triangle I have specified that θ2 is equal to θ1. And you know that under the paraxial approximation where we have assumed that the angle θ1 is very small, we can write that tan of θ1 is approximately equal to θ1 is equal to R2 minus R1 over capital L. So from this triangle you can see that the tan of θ1 is R2 minus R1 over capital L. So rearranging them, so writing tan of θ1 is equal to θ1 and solving this equation for the value of R2, we have R2 is equal to 1 times R1 plus capital L times θ1. This is equation number 4. So this gives the value of the R2 value as a function of R1 plus also as a function of the separation between the two planes, that is the Z2 plane from the Z1 plane. The separation is represented by capital L, and also in terms of the initial angle of the ray, which is θ1. So R2 you see that is an unknown quantity which has been specified in terms of the known quantities 1 times R1 plus capital L times θ1. The second equation is θ2 is equal to θ1. So we can write that equation is θ2 is equal to 0 times R1 plus 1 times θ1. As given in equation number 5. So we have two equations, R2 equation and we have θ2 equation. So we can also write them in terms of the matrix. So combining the last two equations in terms of the matrix form, we have the unknown matrix is on the right hand side, then the matrix 1 capital L 0 and 1 is a matrix that is a characteristic matrix of the free space propagation. So free space propagation has a matrix 1 is a 2 by 2 matrix containing 1 capital L 0 and 1 as the elements, and then we have R1 and θ2 as the output elements. As the output, as the matrix which has known quantities, that is R1 and θ1 are known. And you see that for the free space propagation, the capital L, which is the separation between Z is equal to 1 plane and Z is equal to 2 plane, the capital L is also known. So substituting these values and solving, we know the value of R2 and θ2. Now let's discuss a slightly tricky situation of the free space propagation in which array is incident on the plane Z is equal to Z1 from a medium of refractive index N1 and enters a medium of refractive index N2, and then again it will leave the medium and will enter into another medium of the same refractive index N1. So let me explain the figure first of all. So this is figure number 3, says free space propagation of array between two planes. We have Z is equal to Z1 plane, we have Z is equal to Z2 plane, we have also shown the Z axis, and the ray you see that enters the Z1 is incident at the Z1 plane from the material with a refractive index N1. The value at the Z1 plane is R1 and θ1. Then there is a free space propagation of the ray between the plane Z is equal to 1 and Z is equal to 2. So you see that the light will travel straight, but you see that since the refractive index of this region, which is the free space propagation, has a refractive index N2, so of course the angle will be changed, but the value of R1 prime will be the same as R1, but of course the θ1 prime will be different from the θ1. So you see that I have shown an angle θ1 inside this one, but this is not θ1, but this is actually θ1 prime. So we have R1 prime which is equal to R1, and we have θ1 prime which will be connected to the value of θ1 through the Snell's law. And similarly this light which is inside the free space propagation region will travel straight, and then it will hit the plane which is the Z is equal to 2 plane, and then of course the beam will emerge out into another medium with the refractive index N1. So you see that the beam, since n2 is greater than n1, the beam will diverge out, and of course when the beam will hit the z2 plane, it has a coordinate r2 prime and theta 2 prime, and when it will exit the z2 plane into the medium of refractive index n1, the known parameters the parameters of the beam will be r2 and theta 2. So again, from the triangle you can see that the base of this triangle, which is formed in the free space region, has a base which is delta z is equal to capital L, and the perpendicular side has a distance, has a length which is equal to r2 minus r1. So now we are going to solve this equation. So you see that in this free space region you can say that theta 2 prime is the same as a theta 1 prime, because the light has traveled straight without any bending, so the theta 2 prime is the same angle as a theta 1 prime. But you know that you need to apply the Snell's law at the z is equal to 1 plane in order to correlate theta 1 prime to the value of theta, and similarly you need to apply the Snell's law at z2 plane in order to correlate the value of theta 2 to the value of theta 2 prime. So let's discuss a slightly tricky situation of a free space propagation in which a ray is incident on the plane z is equal to z1 from a medium of index n1 and enters a medium of index n2, and then it will leave the z is equal to 2 plane and will again enter into the same medium, that is the medium with refractive index n1. The ray then leaves the medium at the plane z is equal to z2 and enters into the medium of refractive index n1. The situation is elaborated in figure question 73.3 as shown in the figure. The ray coordinates just before z is equal to z1 plane are r1 and theta 1, and just after the z is equal to z1 plane, the coordinates of the ray represented by r1 prime and theta 1 prime, where we have r1 prime is equal to r1, as you can see from the figure that r1 has the same height as r1 prime is equal to r1, but you see that in order to find theta 1 prime is related to theta 1 through the Snell's law, which is n1 sin theta 1 is equal to n2 sin of theta 1 prime, which under Paraxial approximation takes the form that is n1 theta 1 is equal to n2 theta 1 prime, because we have assumed the Paraxial approximation, and we can write theta 1 prime is equal to n1 over n2 into theta 1. So you see that we have, if you look at the plane z is equal to 2 plane, at the z is equal to 2 plane you have the value for r2 prime is the same as r2 prime will be the same value will be equal to the r2. So r2 prime is equal to r2 because the height at the point of intersection of the z2 plane is the same. So r2 is the same as r2 prime. So this is what we have written. And you know that in order to calculate the theta 2 in terms of the theta 2 prime, we have to apply the Snell's law. So again, n2 into sine of theta 2 is equal to n1 into sine of theta 2. So n2 sine of theta 2 prime is equal to n1 sine of theta 2. So under the Paraxial approximation, we have n2 into theta 2 prime is equal to n1 into theta 2. Solving for the value of theta 2 prime, we have theta 2 prime is equal to n1 over n2 into theta 2. Now r2 prime and theta 2 prime is related to r1 prime and theta 1 prime through the equation this one. So we have r2 prime is equal to 1 into r1 prime plus L into theta 1 prime, and similarly theta 2 prime is equal to 0 into r1 prime plus 1 into theta 1 prime. So actually these are the same set of equations that we have written actually for this setup. So both equations are the same. But of course the variables are different. And similarly we can write down r2 in terms of r1, that is we can write r2 in terms of r1 through the relationship that r2 is equal to 1 into r1 plus n1 over n2 into capital N into theta 1. So this is what we are relating r2 with r1. And similarly theta 2 is equal to 0 times r1 plus 1 into theta 1. because we have obtained the value of these quantities over here, because you see that we have obtained these equations and we have substituted the value of theta 1 in this equation from here, that is from equation number 1 we have used the value of theta 1 prime, and in equation number and similarly for the value of theta 2 prime we have used this equation, that is n1 over n2 into theta 2. And similarly we can use the value of we have used the value of r1, that is r2 prime is equal to r2, and similarly r1 prime is equal to r1. So making all these substitutions in these two equations and rearranging and solving for r2 and theta 2, we obtained these two equations given in equation number 13 and 14. And again writing them these two equations in terms of the matrix form, we have r2 theta 2 as unknown in the form of a matrix with unknown quantities is equal to the matrix of the optical system with the elements 1 n over n2 into capital L, then 0 and then 1 are the elements of the matrix, and then r1 and theta 1 are the known quantities in the form of the matrix. So you see that this is the difference between them, that we have for this system we can find out r2 and theta 2 in terms of r1 and theta 1, and then we have arranged them in the form of a matrix, and then of course the matrix is this one. So this is the matrix of the system of the figure that I have just shown. Next we discuss the case of a thin lens. The optical axis of the lens coincides with the z-axis. Two parallel planes tangent to the lens surfaces at the points where the z-axis pierces the lens surfaces are drawn. Let me show you first the geometry of the propagation of a ray through a thin lens. R1 is the ray which is incident on the thin lens at the plane z is equal to z1. R2 is the emergent wave from the thin lens at the plane z is equal to 2, and it has a value R2 at the value z2 plane. So we have two planes, z1 plane and z2 plane. These two planes are tangent to the plane to the lens surfaces. So z1 is tangent to the left hand surfaces and z2 is tangent to the right hand surfaces of the thin lens. The ray r1 makes an angle theta 1 and the ray r2 will make an angle theta 2 with the z-axis or with the optical axis of the system. The z-axis and the optical axis in this case are the same because both are passing through the center of the lens. So you see that here in this case r1 is the value at the tangent plane at the location z1, and r2 is the value of the outgoing beam at the plane z2, and r1 and r2 are at the same height because the lens is thin. There will be no drastic change between the values of r2 and r1. So we are setting that r2 is equal to r1. An incident ray r1 is incident on the lens from coordinates with coordinates r1 theta 1 at z is equal to z1 plane. The ray after passing through the lens is represented by r2 with coordinates r2 theta 2 at the z is equal to z2 plane. As the lens is thin, so we can write that r2 is the same as r1. A ray r1 appears to emerge from an axial point on the optic axis located at the distance p from the lens center. Similarly, the ray R2 appears to focus at an axial point on the optic axis located at a distance q from the lens center. So you see that in this center you can regard that P, that light that the ray R1 is coming from the point on the optical axis located at a distance P from the center of the lens, and R2 will intercept the optical axis or the Z axis at a location which is at a distance q from the lens center. So P and Q may be regarded as the object point and object point distance and the image point distance from the center of the lens. Okay, according to the sign convention, theta is measured positive, whereas theta 2 is measured negative. From the geometry of the figure shown in equation number 4, we can write that theta 1 is equal to r1 over b, because here we have used tan of theta 1, and tan of theta 1 has been approximated as equal to theta 1 because we are using Paraxial approximation. And similarly here we have used in the second equation, we have used tan of theta 2 is equal to r2 over q, and again you see that we have used tan of theta is equal to minus tan of theta 2 is equal to minus theta 2 due, and negative sign is due to sign convention. And here we are summing up theta 1 plus minus theta 2, and we have summed up the relevant quantities on the right hand side, and we have taken r1 as common because r2 is the same as r1, and within parentheses we have 1 over p plus 1 over q. This 1 over p plus 1 over q is nothing but is equal to 1 over f, where f is the focal length of the thin lens. And this is what we have represented on the rightmost side of equation number 17, that theta 1 plus minus times of theta 2 is equal to r1 over f, as shown in equation number 17. Thus the transformation through the thin lens can be written as r2 can be written as 1 times r1 plus 0 times theta 1, and similarly from here solving this equation for the value of theta 2, we can write that theta 2 is equal to minus 1 over f into r1 plus 1 times into theta 1. So these two equations can again be written in the form of the matrix. So r2 and theta 2, which are unknown quantities, in the form of the matrix is equal to the matrix of the thin lens, which is 1 0 minus 1 over f, and again 1, and then we have the matrix which with the known quantities r1 and theta 1. So if f is greater than 0 for a convex lens, and f can be substituted as negative quantity if we have a concave lens. So this is the equation of a thin lens, that is a light passing through the thin lens. Then you should have a matrix like this one, which is shown in equation number 20. Now we are going to discuss, next we consider the case of a concave mirror of a radius of curvature capital R, where capital R is taken as a negative because the center of the curvature is located to the left of the surface. This is the surface, and its center is located on the right hand side of that surface, which is shown over here. So you see that this, since the since the center of curvature is located to the left of the surface, the incident, so that's why the radius of curvature will be taken as negative. So for those surfaces in which the center of curvature or the lie, or the radius of curvature will be to the right side of the surfaces, then those radius of curvatures will be taken as positive. But in the current situation, we will take capital R to be negative. The incident ray R1 and the reflected ray R2 are shown. Z1 is the axis for the ray R1, whereas Z2 is the axis for the ray R2. You see that we have Z1 axis. This Z1 axis will be the axis for the ray R1, and since R2 ray is going backward, so it has a Z axis which is represented by a Z2 axis, and in principle Z2 axis is negative times the Z1 axis. So theta 2 is negative because R2 needs to be rotated clockwise to coincide with the Z2 axis. So here theta 2 again will be taken as negative, because if you want the ray R2 becomes parallel to the Z2 axis, you need to rotate it in the clockwise direction. So theta 2 is taken, so theta 2 is negative. The two parallel planes Z1 and Z2 shown in figure. You see that here we have to rotate R1 in the clockwise direction, but you see that we have the Z1 axis, and for R2 to coincide with the Z2 axis, we have to rotate it although in the clockwise direction, but you see that this is Z2 axis, which is opposite to Z1 axis. So here theta 2 will be taken as negative. The two parallel planes Z1 and Z2 shown in figure 4 now coincide in the geometry shown in figure number 5. So there will be the geometry shown in figure number 5 will also coincide to the geometry shown in figure number 4. The condition is that R2 is equal to R1 is satisfied for the both cases shown in figure number 4 and figure number 6. So you see that here we have, if you look at this geometry, R1 is the same as R2. Similarly for this geometry, the value of R1 and R2 are the same at the surface of the object, at the surface of the optical element, as we have also written on the top of that one, that R1 is equal to R2 at the Z is equal to Z2 plane, because here Z1 and Z2 plane coincide with each other. But you see that the difference between this analysis and this analysis is that here we have F, but you see that for this geometry, that is for the concave mirror, the relationship is that the focal length can be substituted as capital R by 2. So substituting the value of F is equal to capital R by 2, we have this figure. That is, we have this matrix that is R2 theta 2 on the left hand side is equal to 1 0 minus 2 over R and 1 and R1 and theta 1, because here we have used the value of R to be a negative quantity. So using the value of F is equal to minus R by 2, then it becomes equal to positive quantity. So you see that here you should take as a positive quantity over here, because we are using F is equal to R by 2, but we have to use, since R is a negative quantity, we have used F is equal to minus R by 2. So please make a correction that it should be plus 2 over R, because if this is minus 1 over F, then you need to put the value of F which is equal to minus capital R by 2, because for this geometry we have to take R to be negative. So that's why we are using F is equal to minus. So here it should be a positive quantity. Next we derive the ray matrix for a refracting spherical surface of radius of curvature capital R greater than 0. So here we are now considering this geometry. In this geometry you can see that this geometry has a center of curvature which is on the to the right side of this surface. So R will be taken as a positive, that is the radius of curvature will be taken as positive. So let me explain this geometry first of all. You can see that the ray R1 is incident at the point B located on the surface, where you have R1 and R2, both are the same. The ray is incident from a material with the refractive index N1, and it will the ray after refraction from this matrix, from this surface, will enter into the material of refractive index N2, and the Z axis has been shown, which is passes through the center of this surface. And you see that we have the figure, we have the two triangles, which is one triangle ABC, the other triangle is C, B and D. And you can see that we have angle theta t located somewhere. We have also angle theta 1 and theta 2 with the Z axis. So we have shown theta 1 and theta 2. We have shown angle theta 1 which the ray R1 makes with Z axis, and we have theta 2 which the ray makes with the outgoing ray makes with Z2 as Z axis. And you see that phi is the angle that the dotted line, and the dotted line is actually a perpendicular line, a line that makes an angle 90 degree to the surface at the point B. So this normal line represented by capital N has been extended backward, and it hits the optical Z axis at the point C. So it makes an angle phi with that one, and this C point is located at a distance capital R, because any tangential line through the surface when extended will pass through the center of curvature of the surface. So this capital R is the center of curvature, is the radius of the curvature, because it is a distance to the vertex of this surface from the center of this curvature. And theta t is what we have given. We have also specified, you see, theta t. So look at carefully the locations of the angle theta 1. Theta 1 we have specified at two different locations the value of theta 1, and similarly we have represented the value of theta 2 at two different locations, and then we have theta t also shown over here. And theta 2 is actually the angle that the ray R2 makes with the tangent line, which is represented in dotted form. And notice also the location of the refractive indices. Before on the left hand side of this surface, the material has a refractive index n1, and towards the right hand side of this surface the material has a refractive index n2. And the caption of this figure is the propagation of a ray through a convex spherical refracting surface of radius of curvature capital R. Okay, next we derive the ray matrix of a refracting spherical surface of radius of curvature r greater than 0. An incident ray R1 is incident on the surface making an angle theta I with the normal n. The transmitted ray R2 makes an angle theta t with the same normal. So theta I is the input angle that the ray R1 makes with the normal to the surface at point B, and theta t is the angle that the transmitted, T stand for transmitted, that the transmitted ray makes an angle with the normal. So you see that, notice the position of theta I. Theta I is the angle that the input ray, that the incident ray R1 makes with the normal, and theta 2 is theta t, which is the transmitted angle, is the angle that the outgoing ray R2 makes with the normal to the surface. Okay, an incident ray R1 is incident on the surface making angle theta I with the normal capital N. The transmitted ray R2 makes an angle theta t with the same normal. Theta 1 and theta 2 are the angles of the ray with the z axis or with an axis parallel to the z axis. The normal line makes an angle phi with the horizontal axis. Look at the location of angle phi. This normal line makes an angle phi with the z axis. By sign convention, sin theta is measured positive, whereas theta 2 is measured negative. The incident ray is located in a medium of refractive index n1, and the transmitted ray is located in a medium of refractive index n2. Snell's law at the interface is given. So you see that this is the interface at the point B. Point B provides you the interface between the two regions, that is the region having refractive index n1 and the region having refractive index n2. So the point B is a general point on this surface which provides which is a point on the interface between the two surfaces, between the two regions. So the ray is located in a medium of refractive index n1, and the transmitted ray is located in a medium of refractive index n2. Snell's law at the interface gives n1 sin theta I is equal to n2 sin theta t, because you see that the angle in the Snell's law are measured with respect to the normal, and you see that under Paraxial approximation we can write this equation as n1 theta I is equal to n2 theta t as shown in equation number 22. We need to express theta I, theta t as a function of theta 1, theta 2 and phi, because you see that we have to represent these two angles, that is the theta I angle and the theta t angle, in terms of the parameters of the system, and the parameters of the system are the angles theta 1, theta 2 and phi. Consider the triangle CBD in figure 6. CBD. So C, B and D. So look, consider this figure. So in this figure we can write that angle of 180 degree minus phi plus angle theta t, it should be plus angle theta 2, because the sum of three angles is equal to 180 degree. Actually in this triangle we have summed up all the three angles. The angle at point C is 180 degree minus phi, the angle at point B is theta t, the angle at point D is theta 2. But you know that according to our sign convention we have to use the value of theta 2 as a negative quantity. So you see that in this figure we have angle 180 degree minus phi plus angle theta t. So according to math it should be angle plus angle theta 2, but according to our sign convention in optics we are using minus angle theta 2, and the sum is equal to 180 degree. So you see that solving this equation for the value of theta t, we get theta t is equal to theta 2 plus phi. Now consider the triangle ABC, this triangle A, B and C. So here we have the angles, which is angle theta 1 plus angle 180 degree minus theta I plus angle phi. You see that only the angle which is of optical interest is the angle theta 1, and theta 1 according to our sign convention is already is a positive angle. So angle theta 1 is positive. The rest of the quantities are not optical angles. So we have angle 180 degree minus theta I plus angle phi. We have summed up all the three angles in the triangle, and the answer is equal to 180 degree. So solving this equation for the value of theta I, we have theta I is equal to theta 1 plus phi. So you see that now we have represented our angle, transmitted angle theta t in terms of the parameters which are the desired parameters. We want to use these parameters theta 1, theta 2 and phi as our input parameters. So we have theta t is equal to theta 2 plus phi as in equation number 23, and similarly from equation number 24 we have theta I is equal to theta 1 plus phi. So substituting in equation number 22 the values of theta I and theta t from equation number 24 and 23 we finally obtain. So you see that this is equation number 22, and here we are substituting the value of theta t and theta I obtained respectively from equation number 23 and from equation number 24. So substituting those values over there and solving that equation for the value of theta 2, we get theta 2 is equal to minus times of n2 minus n1 over n2 into capital R, and outside this parenthesis we are multiplying it with R1 plus n1 over n2 multiplied by theta 1. And you know that from this geometry it is obvious that R1 is equal to R2. So we can write another equation, that is R2 is equal to 1 times R1 plus 0 times theta 1. So we have the value of R2, we have the value of theta 2. So we can write down, we have expressed these R2 in terms of the value R1 and theta 1, and similarly theta 2 has also been expressed in terms of the R1 and theta 1. So we can express them in terms of the matrix. So in this matrix on the left hand side we have the matrix with unknown quantities R2 and theta 2, and on the right hand side we have the parameters of the matrix which has element 1, 0, then minus within parentheses we have n2 minus n1 over n2 into capital R, and then we have the last element which is n1 over n2, and then of course the other matrix which has known variables R1 and theta 1 is another matrix. So you see that this is the matrix representation for the case of this geometry, that is for the case of a convex spherical refracting surface. So this is a refracting surface in which the light will enter, in which the light will incident on the surface and then will pass on to the right side of the surface. So for this geometry we have shown that this is the relationship. In equation number 75.6, that is in this equation, in this figure, we have considered a convex spherical refracting surface and obtained the result given in equation number 27. But for the case of concave refracting surface, spherical surface of radius of curvature minus r, the matrix transformation will be given as in equation number 28. Because we have replaced in this equation by capital R will be replaced by minus r, so that we can write down this matrix for the case of concave spherical refracting surface. So this is the matrix for that surface. Now, so you see that we have discussed what we have discussed so far. We have discussed the general transformation of the matrix for any general system. For example, this one, for example this, This is any general optical system, and for that one we have devised our matrix through. First of all, we wrote down two equations, then we wrote down the matrix for that general system. And you see that A, B, C, D will be the elements of the optical system, and these elements will vary from optical system to optical system. However, the position of R1 and theta 1 and R2 and theta 2 will remain the same. Only we need to find out the value of A, B, C and D. And you see that we have solved this free space propagation between the two planes, and for that one we have obtained this matrix, where capital L is the separation between the two planes. Then we have solved this geometry, which is a little bit tricky matrix, in which the light will enter, will hit the plane Z1, and then will enter into another material having refractive index N2, and then will leave into another material having the same refractive index N1. So outside the region of Z1 to Z2, the refractive index is N1, and within that region, that is between the region bounded by Z1 and Z2, the refractive index N2. And for this system, we have also solved the matrix which we have obtained over here as in equation number 15. Now you see that we have also solved the case of thin lens, in which two rays, R1 is incident at a plane Z1, and R2 was emergent ray from the lens. And you see that we have two tangent planes to the surface of the lens. One is the tangent plane located at Z1, the other tangent plane is the Z2 plane, and using these two planes we have made the calculations, and the matrix that we have obtained is this one. Then we have used this matrix in order to obtain the matrix for the concave mirror of radius capital R. Since this is a concave mirror of radius capital R, and the center of curvature is lying to the left of this surface, so R will be taken as negative. So here for this geometry, R is negative. But we are using the matrix, this one, in order to find out the matrix for that quantity, because for that quantity F will be replaced by capital R by 2. Because if you look at the rays, the ray R1 will pass through, will hit the surface where R1 is equal to R2, and this ray will also pass through the radius of curvature or the center of curvature of this surface. So that distance will be equal to, the focal will be equal to F by, so this distance is equal to, F is equal to R by 2. So using that value we have obtained this matrix. But you know that here if you replace F by minus R by 2, then it should be a plus sign. So this should be a plus sign for the case of this matrix, because I think that I have forgotten to change over here. But you see that if this minus is if there is a minus sign with 1 over F, then you need to replace F by minus capital R by 2 for this geometry, and then you obtain the positive sign with this one. Okay, then we have solved the case for this geometry, which is actually a convex spherical refracting surface. And for this surface, since the radius center of curvature is lying to the right side of this surface, so capital R will be taken as a positive quantity. So you see that here we have done simple mathematical tricks, and then we have obtained the matrix for that for the case of convex refracting surfaces also. So in figure number 6, we have considered a convex spherical refracting surface and obtained the result given in equation number 27. But for the case of concave refracting spherical surface of radius of curvature minus R, the matrix transformed will be given as. So replacing capital R by minus R for the case of concave refracting spherical surface, we obtain this result. So you see that once we have obtained the result, we just take care of the sign conventions of the radius of curvature of these surfaces, and then with appropriate sign convention we can immediately write down the matrices for our desired optical systems. Now we discuss the general characteristics of ABCD matrices. So let's discuss the general characteristic of these matrices. That is, the matrix that we write for any general optical system the matrix is written in the form of this one. That is, the matrix contains elements A, B, C, D. That's why it is called ABCD matrix. So here we are actually going to briefly summarize the characteristics of the ABCD matrices, which are very important to remember. So next we discuss general characteristics of the ABCD matrices. Number 1, all ABCD matrices are unitary, that is, have determinants equal to 1, provided the input and output planes are located in a medium of the same refracting index. So this condition is important, same refractive index. For example, look at equation number 28. It is not unitary because the determinant is not equal to 1. But if you set n1 is equal to n2, then of course it becomes a unitary matrix, because we are doing the calculations in the same material. So this is important. So if you are doing the calculations for the input and output in the same material having the same refractive index, then of course the matrices will be unitary. The ABC matrices in equation number 27 and 28 are not unitary, whereas the ABC matrices in equation number 6, in equation number 15, in equation number 20 and in equation number 21 are all unitary matrices. So let me discuss 6. Where is equation number 6? So you see that this is equation number 6. This matrix, you see that this matrix is unitary because it has a determinant equal to 1. Then equation number 15. This you see that this is the matrix having determinant equal to 1. Again unitary matrix. Look at this matrix. Again it is a unitary matrix. 21. Again it is a unitary matrix. So you see that sometimes we have unitary matrices, sometimes we have non-unitary matrices, and the difference is what I have cleared over here. The point 2 is the composite ABCD matrix of a composite optical system is calculated by multiplying ABCD matrices of individual optical systems in opposite order as explained below. So you see that in the above calculations we have discussed only one matrix at a time. That is, we have discussed only one optical system at a time. But if our optical system contains many optical elements, then we need to write the ABCD matrix for each component, and then we have to multiply them in the order given below. So ABCD of a composite system consisting of many optical elements is equal to the ABCD matrix of the nth component multiplied by the ABCD of the n-1th component multiplied by the ABCD of the second component multiplied by the ABCD of the first component. And this first component is the first component that is encountered by the ray. The first component through which the ray will pass will be the first component, and then after passing through the first component the ray will pass through the second component, and so on. So you see that we have to multiply them in this order, that is in the opposite order. That is, the last matrix will be written first at the first position, as we have written the nth component of the matrix, and similarly the matrix multiplication is done in order to find the ABC matrix of a composite system. The third condition is that the A prime, B prime, C prime and D prime matrix of a given optical system for backward propagation. You see that here we have labeled A prime, B prime, C prime, D prime because this represents a matrix for a backward propagation system in which the light will travel towards Z2 axis or minus Z2 or minus Z1 axis. So for such a matrix can be obtained by simply interchanging the A and D elements of the ABCD matrix of the forward propagation as explained below. Forward propagation means that the light, that ray is traveling towards right, and backward propagation means that the light is traveling towards left. So you see that we have A prime, B prime, C prime, D prime is the matrix representing that the ray is traveling towards the left is equal to the matrix ABCD for the forward propagation matrix in which we are making this condition that we are replacing A with D or D with A, and the final matrix is given by D, B, C, A. So our A prime, B prime, C prime, D prime obtained from the forward propagation matrix is equal to D, B, C, A, in which we have replaced, interchanged A and D. The fourth point is ABCD matrix of an optical system can be used to correlate the radius of curvature of the incident input spherical wave Ri and the radius of curvature of the emerging output spherical wave R0. So let me read again. The ABCD matrix of an optical system can be used to correlate the radius of curvature. So here important thing is that we can correlate the radius of curvature of the incident input spherical wave having radius of curvature represented by capital Ri and the radius of curvature of the emerging output spherical wave represented by R0. We can find out the relationship between R0 and Ri using ABCD matrix algebra. For example, consider an optical system in which P0 and P0 prime are the conjugate point sources, with R1 and R2 conjugate rays emanating from these or going or focusing towards them. For example, R1 is emanating from P0 and R2 is going towards P0 prime. So P0 and P0 prime are the images of each other. So that's why we call them as conjugate point sources. And the rays respectively will be regarded as conjugate rays. They are related to the radii of curvature through the relationship that Ri is equal to, for example, if you apply the tan of theta 1 to the left, to the triangle on the left hand side of the optical system, you will get tan of theta 1 is equal to R1 over Ri. And using a Paraxial approximation, we can represent tan of theta 1 as theta 1, and solving that equation for the value of Ri, you will get Ri is equal to R1 over theta 1. And similarly, on the right hand side, if you consider a right angle triangle on the right hand side of the optical system after the Z2 plane, you can write tan of theta 2 is equal to R2 over R0, and using and substituting tan of theta is equal to R0, and solving this equation we get R0 is equal to R2 over theta 2. So the propagation, so this represents a propagation of a spherical wave through any general optical system confined between the two planes Z is equal to 1 to Z is equal to 2 plane. And there are two conjugate point sources P0 and P0 prime. The ABCD transformation equation for a general optical system as shown in equation number 7 are given. So you see that from equation number 7 we have the general system was R2 is equal to A times R1 plus B times theta 1, and similarly the second equation was theta 2 is equal to C times R1 plus D times theta 1. You see that these two equations are the equations on which our matrices are based. And of course, you are familiar that A, B, C, D are the parameters of the matrix. Now here we have the value of theta 1 from here. You can find out the value of theta 1 from this equation. So we have theta 1 is equal to R1 over capital I, and you can find out the value of theta 2 from this expression, which is equal to theta 2 is equal to R2 over R0. So we are replacing theta 1 shown in the red with the value R1 over Ri, and in the blue we have theta 2 in the blue represented in equation number 32, and we shall replace theta 2 by the value R2 over R0. So making these substitutions in equation number 29 and equation number 30 respectively, we obtain R2 over R0 is equal to C times R1 plus D times R1 over Ri. And solving this equation for the value of R2, which is R2 is equal to R0 times into C R1 plus D times R1 over Ri. From equation number 30, equating R2 from equation number 31 and equation number 32, and after simplification we obtain. So you see that we are now equating Okay, equating R2 from equation number 31, R2 and equation number 32. So equating the value of R2 from equation number 31 and equating it with the value of R2 from equation number 32. So we get this value. So you see that this is R2 from equation number 31 and this is R2 from equation number 32. Equate the value of R2 from equation number 31 to the value of R3 in equation number 32 and then solve the resulting equation for the value of R0. You get R0 is equal to A times Ri plus B is divided by C times Ri plus D. So you see that you can correlate the value of R0 in terms of the that is the value of the output curvature in terms of the input curvature value Ri through the system element ABCD. And this relates the radius of curvature of the output spherical wave from an optical system to the radius of curvature of the input spherical wave in terms of the ABCD parameters of the optical system, provided the spherical waves are considered under Paraxial approximation. And you know that under the Paraxial approximation means that Ri is equal to R1 over theta 1 and R0 is equal to R2 over theta 2, and these two equations we have already explained. And you see that this R0 and Ri are actually the radii of curvature of the spherical wave. Input spherical wave Ri is the radius of curvature for the input spherical wave, and R0 is the radius of curvature for the output spherical wave. So we can find out, don't confuse these radii of curvature with the radii of curvature of the optical element. So the optical element radii of curvature are different. So these are the radii of curvature of the spherical waves incident on the input on the optical system and output from the optical system. So you see that I have discussed main or major optical systems. I have constructed the ABCD matrices for such optical systems. I have discussed the sign convention during the course of this lecture, and I have also discussed the main characteristics of the ABCD matrices over here. So this completes the answer. So this is the end of slide number 75.